السلام عليكم جميعا. دكتور علي. دكتور علي. ويلكم دكتور لين.
السلام عليكم استاذ احمد، تسمعني؟
اي نعم، الدكتور لين انضم.
اي نعم انضم.
ممكن تتحدث وياه.
اي نعم. دكتور لينشن، بروفيسور لينشن. بروفيسور لينشن. Professor Lynchen, please.
Can you hear me?
Yes, I hear you. How are you, Professor Lynchen?
Oh, okay.
Thank you for attending. Thank you.
Yes.
Okay, we will start after 1 minute. We will start.
Okay.
I will start with presenting you. Then after that, you will start your lecture. Then after that, there is some question and answer.
Okay.
That's it. Okay. Thank you so much. استاذ احمد.
نعم دكتور.
ان شاء الله انا راح هسه ابدي، بس شوف ان الحضور هسه شلون صار عندك.
لا متواجدين. تفضل دكتور.
يا الله. بسم الله الرحمن الرحيم. طبعا نرحب بكم جميعا اخواني واخواتي. ان شاء الله راح ابدي البدايه باللغه الانجليزيه طبعا، وبعدين راح انطي فد نبذه عن المحاضره ان شاء الله. بدايه بسم الله الرحمن الرحيم. Here at Iraq we live and die by our communication successes, failures. On behalf of the College of Engineering, University of القادسية, Iraq, ladies and gentlemen, my name is Ali Abdulhussein Jazam, and I am an assistant professor at the Department of Chemical Engineering, College of Engineering, University of القادسية. I'm so excited to be here afternoon and to have the opportunity to introduce our guest speaker, Professor Dr. Lynchen. The title of the speech for Professor Lynchen is Optical Methods for the Quantitative Measurement of Heat and Mass Transfer in Energy Systems. The talk will focus on two main points. One, quantitative methods of optical flow and interferometry technologies are introduced in this study. The recent optimal methods for precious heat and mass transfer measurement applied in energy fields, the detailed principles, application fields, challenges, and future trends. Let us give some introductory about Dr. Lynchen. Dr. Lynchen is a professor in the Chinese Academy of Science, China. He obtained his B Engineering and PhD from Peking University. He is also granted JSPS, JST, Crest Research Fellow and Assistant Professor in Tohoku University in Japan. His current research topics include renewable and unconventional energy resources, plus supercritical fluids, multi-scale heat and mass transfer, and advanced measurement techniques. In recent years, he has authored more than 120 well-cited international journal papers and/or conference presentations, keynotes, invited talks, books, chapters, including the most famous one on energy conversion, advanced applications of supercritical fluids in energy systems, IGI Global 2017. Dr. Lynchen is a winner of the President's Scholarship, National Scholarship, MOE, Elite Scholar, Young Scientist Award, and many other honors and awards. He received the Innovation Award in 2011 and 2012 and 2014. Elsevier Journal's top 5 most cited paper and Elsevier Excellent Reviewer 2013, 2017. He is also a reviewer and editorial advisor, TPC member, guest editor for many renowned international journals, conferences such as the Journal of Supercritical Fluids, one of the Elsevier journals. On a final note, he is also fascinating individual and we are grateful for his presence among us today. Without further ado, please join me in welcoming Professor Dr. Lin. اخواني واخواتي، ان شاء الله راح طبعا قبل ما يتفضل بروفيسور لينشين بالمحاضره راح اتحدث باللغه العربيه، فنبذه مختصره عن المحاضره. ان شاء الله راح تتضمن المحاضره اهم التقنيات الحديثه المستخدمه في عمليه مراقبه وفحص انتقال الكتله والحراره في الاجهزه المختلفه المستخدمه في الصناعه. طبعا هذا المجال يخص المختصين في مجال الفيزياء وخصوصا البصريات والليزر، وكذلك المختصين في عمليات انتقال الكتله والحراره في الهندسه الميكانيكيه والكيمياويه والمواد. ان شاء الله راح انطي الميكروفون الى بروفيسور لينشين حتى يتحدث لكم. مشكور. Professor Dr. Lin, you hear me?
Yes.
Please kindly ask you to give your speech. Thanking you.
Okay. So I will share my screen.
Yes.
Okay. Okay, so can you see it?
Yeah, we can see and hear you very well.
Okay. So thank you very much, Professor Ali.
Thank you.
And we met in international conference, web-based international conference last month, and I'm very happy to share my study about the optical methods for the quantitative measurement of heat mass transfer in energy system. Indeed, it's very critical about the measurement in heat and mass transfer process. The major parameters such as the temperature distribution, the pressure distribution, and also the concentration parameter and the changes in heat flux. Those parameters are very important for heat transfer energy systems, and also quite important for the chemical reaction or medical and the petroleum engineering and the other even bioengineering. Those measurements becomes more and more important in recent days. So we're very happy to introduce what we are doing for Dr. Ali and your colleagues and students here to share the knowledge and to discuss about this. First, background introduction, I just skip because Dr. Ali has already introduced me a lot. So what we are doing now is, this is the main picture. What we do in China, we focus first on the energy storage system. We use the compressed air energy storage system, which means we compress the air to high pressure and to high density status to store the energy. When we need electricity, we just expand and to generate electricity again. So this is the way we do in energy storage. We use the compressed air. So you can see in the world, we have several kinds of a large system that with a capacity higher than 1.5 megawatt. Indeed, in China, the IET-CES, which is the biggest one, we have a 10 megawatt advanced compressed air energy storage system. This is what we do, and in the energy sector, we try to use many technologies to enhance the energy storage efficiency and also the stability. This is what we are doing now. And in those systems, to tell the details, we can see we have Energy Storage Research and Development Center in our institute. And what we do to compress the air to supercritical state as we discussed with Dr. Ali in the conference, we do supercritical fluid system. Supercritical fluid system use the air as a working fluid, and so we can easily get the air from outside for ambient conditions and compress it, and we place heat exchanger to restore the heat when we compress the air. Then the air is stored in the low temperature tank. When it is stored, after that we can use it. This is a basic method that we can have in 15 kilowatt. This is in 2006, and then we have a 1.5 megawatt system. This is in the Langfang city, just 100 kilometers from Beijing. This is what we do now, and we have 10 megawatt system, and also we have now building 100 megawatt system. But this is still very small when we compare it with the energy consumption of a city or a community. This is very small. So this is the fundamental research we do to support the energy storage, the supercritical fluid-based energy storage system. Here is the purely the supercritical CO2 system for energy efficiency improvement. And this is why we use supercritical fluid in the energy storage. This is supercritical CO2. You can see there we have a red dashed line. This line is the Carnot. Carnot efficiency means if we use the Carnot cycle to generate energy, this is the highest efficiency, the theoretical efficiency limit. This is limitation. So for our mankind, we many years ago we use like a geothermal, then we use nuclear, then we use a coal-based turbine cycle, and the efficiency increase with the turbine inlet temperature. However, if we use higher than 500 degrees, we can have a supercritical CO2 indirect cycle. This cycle has a very high efficiency, but if we further increase the temperature supercritical state, we have this green line. The green line means we have to the turbine inlet temperature higher than 100 degrees centigrade. This means we have higher than 60% the energy conversion efficiency. This is very high, and even higher than other traditional method, gas turbines, other kinds. So this is very critical for us to develop a high temperature and with highly stable system for supercritical fluids. This is very critical because we found it. It is now applied in many systems, such as this is the solar tower, and maybe nuclear, and also power generation, geothermal system. And also we have small systems like some kind of a satellite system we do to do the cooling or heat removal. And this is the fuel cell and the MEMS chip cooling. And also for nano particle synthesis, those ones are chemical applications, such as we do the modifications of a surface. The reaction happens in supercritical state, and in chemical reaction mixing process using supercritical environment. This are maybe more related to your study in chemical aspect. And also we can find the major problems is first is the stability, because we have very high pressure and temperature. So the stability becomes a problem, the safety. And the second one is what is happening when we have a supercritical state? What is the local process we do if we found for supercritical curves that may happen on this is the critical fluids, the local process. This is water. If we change the temperature a little bit or the pressure a little bit, we can find a very large fluctuations in the specific heat, or the density, and also the thermal conductivity. This means we have very large local changes for supercritical fluids. So this is you can find this is one example we have made in our laboratory, that we constructed a supercritical fluid based. We use a supercritical CO2, supercritical fluid based solar collector. This is designed for around 15 megapascal system. So we have a simple heat exchanger. This is solar panel. Then it goes to the fluid heated, then goes to the heat exchanger. We first use the water heater to heat water in the tank. Here you can find that we have a tank. Then the fluid is cooled down and then goes back to the solar heating up process. So this is a basic kind of a circulation flow for supercritical states. However, if we found for supercritical states, the fluid is very sensitive. Usually we measure the collector efficiency. It can exceed 200%. It means the parameters measurement of the temperature and the efficiency parameter, mainly the temperature and pressure, will be wrong if we found the fluid goes across a critical point like this part. This part means the measurement is very difficult. Why it is very difficult? We can find in many applications. Both those systems are very similar for us to check what is a supercritical fluid and a supercritical systems. The core systems we found, I have introduced those. Or you can use supercritical state like the solar tower or the nuclear core or power generation or geothermal. Those systems we can find very important design failures or the local heat transfer abnormalities. Like maybe I can take it for example. We have a very small channel. It's in micro size. In micro size, if the fluid is heated locally, it will have a very large vortex through the channels. This is usually happens when we have phase change problems in the such as in a nuclear core. The very sudden heat up of a fluid or the boiling process will form very large heat flux or density changes. This is what we can find in supercritical systems. The local mixing process and also the solar collector efficiency high peaks. This is very important for us to estimate the system efficiency and its behaviors to improve the performance of the system. So here we introduce, as Dr. Ali introduced, that we will introduce two kinds of optical methods to measure those heat transfer, mass transfer, and the temperature field of the heat mass transfer process. One is the interferometer system. Interferometer system means we use a laser system to measure the heat process, because the density field or the temperature field of a sample, H of the sample. This is test beam, this is the reference beam. Then if the test beam goes through the testing sample, so the temperature field has a correlation with the refractive index of the fluid. This means that if we have interferograms here, then we can measure the accumulated changes in the optical length. Then we can have the interferogram patterns. By analysis of the patterns, we can recover the fluid property changes of a temperature or density or concentration here in the sample. This is the laser measurement. And also we have another kind. This one is the luminescent molecule method. Because many people, I guess, from Dr. Ali, from chemical fields, so you may be very familiar with those kinds of molecules that is quite sensitive to temperature or pressure. This means if we have excitation light, like the purple one, excitation light to the surface to get in contact with the luminophore, this molecule, and then it will be excited. After excited, it will emission of the light. This is light usually falls in the visible light region, and so we can have a camera, CCD camera, to measure the light intensity changes of a surface. This means we have this kind of a correlation of the intensity parameter and also pressure or temperature parameter in this way, we can recover the surface temperature distribution or pressure distribution. So this means if we have those kinds of system, we can measure here the concentration or the temperature, and here we can measure the surface temperature and also the pressure distribution. This is very interesting that I will show you more examples of what we can measure using this kind of systems. This is one we do use interferometry to see the invisible part. Which what it means that invisible part? It means usually if we do optical measurement, we can measure about the intensity and also the wavelength. That means the energy level. However, we still have the third parameter. The third parameter is the polarization of light. So the polarization of light, usually the eye of our human beings, we cannot see the polarization of light. We can see the darkness of the light. And this means we see the intensity, and also we can see different colors. This means they have different wavelengths. However, for the light, it has the parameter of polarization. So this we cannot see it by our human being eyes, but by many animals like a fish. They can clearly visualize the polarization. This explains we cannot easily get a fish. This is very important that they can easily get escaped. However, we use these kind of techniques. We can measure many interesting things. This is one example that we use the interferometer system, and then we measure very small channel. This is 15 millimeter channel, and inside of a 3 millimeter and 4 millimeter square region is filled with nitrogen in 8 megapascal. This means we can easily measure the supercritical state. If we have a 0.5 degree temperature difference here on this surface, the 4 millimeter surface, so the fluid soon becomes curved. This means this is the interferogram means the density gradient parameter. So we can measure very clearly the convection process inside a chamber. This is very important. If we have sensor that we can get the point temperature, then we can recover the field temperature. This is the quite powerful way that we can measure. So this helps explain what is the invisible part. I explained the polarization of light. It means the polarization means that in the light, usually the different polarized, not circular, but it has different angles if we compare it with the horizontal surface. So in this case, if we have a polarizer, it allows only maybe the horizontal polarized light to pass through, or it allows only the vertical set of light to pass through. So this means if we have this kind of a filter, or if we have if we have this kind of a reflection surface or the water surface, we can have this kind of process. So we can find a reflected linear polarized light. This is the only one direction and goes back from the surface. So by this kind of we can have many kinds of a polarizing filter, like this one, the wire-grid polarizing field. In this field, we can divide the light into different directions, different polarization angles. By this method, we can design this kind of polarizers. Using this polarizer, we can measure maybe 4 different directions, or you can design by yourself by many kinds of polarizing directions. So we can have example to measure. This is recovered from 4 angles, 4-angle system. We can get this is the normal picture by our cell phone and by a normal camera. This is when the polarized light recovered image. We can see very clearly the difference from those pictures. So this means we can visualize the invisible part of the process. So our method is to use this technology to measure what is happening in those systems, and we have to do the data shifting process to recover the system. This is a very simple calculation, and this is example we measured the wine diffusion. So we have this chamber then we have a water surface. We can drop a small part of wine inside, and then it will diffuse from the double side to water side and to the wine side. This is the picture that is changes with the time. So this explains we can measure the mass diffusion process. Very clearly, the mass diffusion process, we measure the concentration field of a process with it evolves with time. This is just a slow case, and now we can measure about the 0.001 second for the quick process. So this we can explain the different diffusion coefficient or the diffusion coefficient of a different. This is different kind of 3 different kinds of wines in China. So you can find this one, the last one, has the highest diffusion coefficient. Indeed, this one is the best seller. This one is the best seller in China. So we can have a very good prediction, and this fits well with the general result of the measurement. And this one is about heat transfer. As we introduced, this is the concentration field measurement. This is a heat transfer measurement. Use this technology, we can design a well thermal insulated chamber to have a low temperature side and a high temperature side. Then we have a natural convection inside this chamber. However, it's now usually we can do numerical simulation to test what is happening inside these kind of chambers, but it's we are rarely seeing this kind of experiment data. So it's quite difficult to visualize the temperature field. Usually we can have a temperature sensors to insert inside the chamber to measure just the point temperature. However, for numerical simulation, we can get this numerical simulation, we can get the parameters, and this is the measurement data. You can see if we cut this curve, the 3 position, we have a very good agreement between the visualized image and also the numerical simulation. So we get one step further to measure about some kind of a reaction process. You can find we have this is a methyl hydrate. Methyl hydrate is some kind of a chemical that it can decompose itself if we lower down the pressure or increase the temperature. This is just like some kind of reactor system you can find in many chemical process. Then we have a thin layer of decomposition film. Then we have the concentration field and decrease, and also for fugacity changes. So this means we can measure the surface reaction by our interferometer system. So the surface reaction process, first we designed this is okay. We can design such kind of a reaction system. You can find we have some kind of diffusion from the solid state to the gas state. So if we divide this with time, you can find with 0.05 seconds the changes is very large. We can get a very clear picture about the diffusion process. So this kind of technology can help us to increase the visibility, and this is the comparison with between experiment and numerical results. We have a very clear agreement of a mass transfer process. So if you have a very critical case that you want to measure the diffusion coefficient or the reaction speed, reaction parameter, so this is quite useful. So we can measure the surface process. Indeed, the spatial discretization is about 20 micrometer or smaller. So this is quite interesting. So we are using this technology to do many kinds of measurement, like the supercritical fluids. And then we use this process. We can design the heat transfer enhancement, like the chip cooling or electronic cooling. We integrated the microchannel chip And then we measure this is a 200 micrometer for white. We measure the temperature drop and the density change through this 200 micrometer channel. So this is the result. We can find very large density changes can be found in our heat transfer cooling process. So this is a measurement result, and also we can have this very high temperature drop due to the 1 megawatt per cubic meter electronic cooling. This helps us to make better design of our system. And then we go to the second part. The second part we can measure the optical flow. What is optical flow? It means we have different kind of methods to measure the optical flow. Means optical method. We have usually we have oil film thickness measurement, and also we have a sublimation mass diffusion measurement, and also we have a pressure sensitive band measurement, and we have temperature sensitive band measurement or skin friction measurement. Those measurements are very simple in aerodynamics or in gas dynamics, and also for the temperature heat mass transfer measurement. In those methods, they have different kinds of governing laws, like Navier-Stokes equation or the mass diffusion equation or the Fick's law. We have different kinds of laws. However, we found the governing equation of those methods are quite the same. We have a G, and we have a tau, and we have a derivative parameter, and those maybe we can change it to different detailed parameters, but the format is very similar. So we categorize this into one general kind of equation to test if the optical generalizes optical flows, and to solve this equation, we can get many interesting things and in our measurement. So first measurement is what we can find. We do real attachment flow. What is a real attachment flow? It means we have a step here, then the flow will go separate and real touch on the surface, and then develop again. Okay, so this is quite simple. We have a very large unstable phenomena here, and we can find is a real attachment point. In the real attachment point, the turbulent effect becomes dominant, and we have the highest heat transfer rate here. Therefore, we have the lowest temperature here. So by this understanding, we can design our luminescent measurement system. Also, we can get very important results that we can have a temperature field here. It changes. The temperature field changes with time. Okay. The temperature field changes with time, and we can get clearly the changes of the figure. And then we have that this is normalized picture, and if we check on the center line, we can get the temperature curve through the center line. Then we can get the real attachment point where the temperature becomes the lowest region. This is quite interesting what we can do, and by the further analysis, we can still get the surface skin friction parameter and also the skin friction streamline to be analyzed. This is maybe related to the fluid dynamics aspect. And also in another method is the luminescent wires that can be used like a tuft on a surface to measure the surface dynamics of fluid flow. If we use this model, to have a flow on a surface, then we have touched some kind of a mini tuft like this one. So we can have very interesting formulas and luminescent ones. We can get clearly the changes of those tufts like small worms on the surface, then we can get the averaged parameters of the flow behaviors. Those technology can be used in the surface flow measurement. It's very useful. So, and we can also do the second thing is to capture the, we have the dynamic tuft movement here, and we have to capture and digitize the movement of the curve. So we can find a very important one. This is a real tuft. This is our capture by our program to get the real movement of those tufts. This is very interesting, and we can detect averaged picture, then projective transformation. Then we project the movement of the real tuft on our surface. Then we recover the behaviors of the tuft. So this is what we do to get the real attachment and also the surface behaviors of a flow. And so this is the many kinds of technologies we use to measure the surface heat mass transfer. I think if it will be quite useful if you do chemical measurement or heat transfer measurement. This is one of the book that we published for the microchannel process heat transfer, and for the near critical and supercritical fluids is published in spring in Germany. So if you can have a good reference, you can get access to it. And this one is the advanced applications of supercritical fluids in energy system. As I said, I'm doing supercritical fluids, so we gathered together the many scientists in the world, like in Russia, United States, and Japan, and Australia, and also from India and China. We get together and write a book. It has a very fundamental aspect into molecular scale. Or we have many kinds of applications of supercritical fluids, which enters the world of nuclear and thermohydrodynamics, heat exchanger, and also for the green chemistry, like to extract chemicals, extract useful parts from the plants, also from the oil, gas, and many kinds of applications of supercritical fluids. And I believe this is the first one book that you can find on the energy system for the use of supercritical fluids. So we have these two professors also helped the writing of the book, and I'm also very thankful that we can still continue the collaboration. And also, if you're interested in those fields, we can still do something together. And this one is about the scientific journals that I'm working with as associate editor of ASME Journal of Nuclear Engineering and Radiation Science. I'm associate editor, and also the Journal of Supercritical Fluids. I'm editorial board member. So if you're interested in supercritical fluid, you can submit your papers to those journals. And so finally, we found that it's very important for the surface measurement, and also for the optical method, that we can get very important information for the heat and mass transfer and the surface reaction flow phenomenon in our experiment, and which will help for our measurement and for numerical study and for better understanding of the heat mass transfer process. Okay, so my talk just finished here, and if you have any question, you can ask me. Thank you.
Thank you so much, Professor Linchin. Thank you. It's a very interesting lecture, and actually I'm not have only one question. I have so many questions I want to ask you. Thank you so much for the second time.
Okay.
Thank you, Professor.
Okay.
Yes, أحمد. طبعا إذا أكو أحد عنده سؤال أنا إن شاء الله راح أبدي
نعم دكتور وياك.
عندي كم سؤال. نعم أنا عندي كم سؤال يعني إن شاء الله راح أبدي أسأل بروفيسور، فإذا أكو أحد رافع إيده أو فد شيء
أنا متابع.
تحب. أي نعم. Yes, Professor Linchin, please. I have a question.
Yes.
Yes. Please, Professor, for nanofluids, is there any problem regarding the measurement as there is a nanoparticles used for the nanofluid? I'm asking about the transparency. Is there any problem with using nanoparticles or nanofluid?
Yes, yes. For the laser system, indeed, it will have some effect for the nanoparticle nanosystem. But we are now trying to do one thing is we use the supercritical fluids, and also we add the nanoparticle inside the fluids to recover solar energy. So we use it in the solar panel. So in this measurement, we tried to make the solution, the concentration becomes very low. This means if we have a high concentration, the refraction or diffraction process of a lot of particle may affect the measurement because the light is diffracted. However, if we limit the concentration to very low, our measurement shows quite a good result. So this is the answer that we have some effect if we have nanoparticles, but if we limit the concentration, we can get some good result.
Oh, okay, thank you. So the problem is can be solved, by the model. Okay. Okay, another question, please. What about if the fluid is colored? How you?
Okay.
Okay, is there is some colors already is there?
Yes. Indeed, if the fluid has some color, this is also possible because it depends on the accumulation of the light optical path in the test sample. So we have to increase the intensity of the light. Yes, intensive light. However, if the fluid becomes fully black or some to some extent even very difficult to visualize, so it will cause some problem. It depends on what is inside the fluid. If the inside the fluid, such as we said, we have a nanoparticle, or we have some kind of material that will absorb the light. This is a major problem. For normal fluid, I think it's okay.
Okay. Yeah, thank you. I'm using the Sol-Gel method. Is it possible to measure the transient phases for that process?
Yes.
And in the same techniques?
You mean the transient? Transient process means it will change with the time.
There is so many methods for imaging recording: interferometry, Schlerin, shadowgraph. But I'm asking, which one is the most accurate or easier? Actually, we are asking about the easier one and have some accuracy is good. Which one? Interferometry, Schlerin, shadowgraph. Which one is?
Yes, indeed. This depends. It depends on what you want to get from the experiment. Yes, from experiment, because the interferometer indeed is directly related to the density itself. if we use shadow graph, it's the first derivative of density, and the Tshilin is the second derivative. So it means it will depend on what you want directly, you know. And in my from my experience, if we want to measure something like the diffusion or surface reaction process, interferometer is quite good.
Excuse me, Professor.
Yes.
Exactly about the reactor. If I'm checking the inside CSTR mixed reactor.
Yes.
Yeah. I want to check the heat and mass changing inside this reactor. Which one is the better? Sorry.
Yes, then I think the interferometer is quite good because it directly gives you the answer.
Yeah, thank you.
Yes, and previously we used the Tshilin to measure the shock wave, the very critical density changes of a surface. That is a high-speed phenomena, and for normal maybe reactor, you can use interferometer, I think.
Actually, I have so many questions, but there is some others they want to ask. Just one question more.
Okay.
Is there any, what about the angle of inclination when we are taking the pictures? Is there any effect for, or something, you have some decision about choosing the angle of inclination? Is it?
For the interferometer system, indeed, we need to have something kind of a 90 degree direct incitation of light. That is necessary, and this is quite important because we usually have a window. We have a window between the sample and the laser light. So if we have some kind of angle, this will affect the light path. If the light path changes, it will have some kind of error in the final interferograms we get. However, if we design the system, we have a reference beam, we have a test beam. If they both have this kind of angle, I think we can check by some kind of additional calculation. We can recover this kind of angle. It depends on the system design of the measurement. Usually, we use the direct incitation of light.
Yeah, thank you so much, Professor.
Yes, if we use I mentioned a second technology about the temperature sensitive and pressure sensitive molecules, then we can measure at any angle.
Then what about if I'm checking for temperature and concentration?
دكتور علي.
Yes. تفضل.
Question from Furqan.
A question? Okay. Please, Professor Linchin, there is a question from the attendants.
Okay.
Yeah.
Okay. Thank you very much. It is Furqan Al-Araji. I'm a doctor of veterinary medicine. It is not my specialization, but it was a very interesting lecture. Thank you very much, Mr. Linchin. I have one question, please. Maybe it is not about the focus of your lecture, but I have a question about the light, please. Did light have a weight? And can we measure the weight of the light or not? And is there a difference between the light, maybe from the sunlight or our light? And what is the difference in the weight of the particles of light? Thank you very much.
Oh, okay. So your question indeed is related to the how do you say, the light itself. The light itself. For our technology, we have maybe for interferograms we just use the interference of each other. This we divide the light, the polarization, but we cannot divide the weight of the light. And but for a second technology about the what is temperature sensitive paint technology, we can do something on this because we have the excitation process. This we used the how to say, the emission, the reaction of the luminescent molecules. It has a different energy level. This is related to the wavelength of the emission. So I think if the light particle has different weight, this means the the energy level will be changed.
Mm-hmm. Thank you very much for interesting lecture. Thank you very much.
Yes.
Thank you. Thank you, Dr. Furqan, for the question.
Okay, thank you.
Another question, Sir Ahmed? Is there any?
No one. Doctor.
Yes. Yeah. Meanwhile, I will ask one question, please, Professor Linchin. I'm asking about if I'm checking in the same time, I'm checking concentration and temperature. Is there any interaction or intervening between the measurement and that means there is some error is affected or coming with the model? Yes.
So you mean the?
Is there any intervening or interaction between the measurement of concentration and temperature in the same time? In the same time, if I'm measuring in the same time.
Oh, okay. I understand.
Yeah.
Indeed, I introduced you about this measurement.
Yeah.
In this measurement, indeed, if we have this kind of a surface decomposition or reaction, indeed we have the concentration field, because we have a mass transfer, mass diffusion process in this direction. And at the same time, we have heat transfer. And because the reaction will have a thermal effect, it will release heat or it will use heat. So the temperature on the surface will increase or decrease. This depends on the reaction. So in this process, as you mentioned, we have the temperature introduced interference, and also the concentration field introduced interference at the same time. Yes, so this is the very critical question for the measurement. So for this kind of process, we can do two kinds of calibrations. First, the first one is we can, and this means we separate the effect of each other. The first one is we have to control the heat transfer. This means we can place a plate on the bottom on the surface of a particle. Then we measure there is no heat transfer or very small heat transfer. We limit it on the surface region. Then we measure the mass transfer. And the second calibration is we find ways to maybe we just make some kind of filter here to limit the mass transfer. We just measure the heat transfer introduced interferograms. Then we can, the third experiment is we measure the heat and the concentration inserted interferograms at the same time. So this is one method we can do to recover the final process of the effect of both reasons.
Thank you, sir. Thank you, Professor Linchin. Thank you. Is there any question, Sir Ahmed?
No one, دكتور.
Okay.
Can end.
Yes.
دكتور ماكو أحد، العفو.
معكم أحد. Professor Lin, please, what about if I'm using which type of laser I have to use?
Okay.
Yeah.
For the measurement, usually we use helium.
Helium, helium, yes. Helium
and the light.
Yeah. Right. Okay.
Laser. Okay.
Okay. Yes. One question
Okay,
is
you can see here.
Yeah. What about? Is there any difference if I'm using the laser? Now I will repeat the question, the same question. Laser Schlieren or rainbow is Schlieren is better, and what is the difference?
Okay, Schlieren is measures the second derivative of density.
Sorry, this question is especially for the reactor. I'm asking.
Okay,
Yeah.
okay. For Schlieren method, I think the Schlieren method should have very very, how do you say, very low concentration, I think, and also the critical surface should be very clear.
Yeah.
Then if we have some kind of mixture or something, large mass measure movement.
There is multi-phase.
Yes.
Yeah, there is multi-phase in the reactor. So
yes, so the Schlieren will be quite difficult, I think.
It's difficult. Just for one phase is simple, can be.
Yes.
And by rainbow or the Schlieren?
Yes.
Yeah, which one? I'm sorry, laser Schlieren or rainbow Schlieren?
Yes, I think rainbow Schlieren can be tried.
Okay, thank you so much. Yeah. Thank you. أستاذ أحمد أكو سؤال بعد ضمن الحضور؟
لا ماكو، لا بالشات ولا
شكرا. شكرا جزيلا طبعا للحضور جميعا. اخواني واخواتي اشكركم جميعا لحسن اصغائكم. Thank you, Professor Lin, for this valuable actually this valuable speech and valuable comments from the attendants. Thank you so much and take care and be safe. Thank you, Professor Lin.
Okay. Thank you very much, and thank you everyone, your questions, and also your very good interest for the measurement and also the heat mass transfer technology. And I think we can continue discussion with all of you in the future.
Thank you. Please, Professor Lin, I hope the cooperation between us will be continue, and we will take the opportunity to ask you to make another maybe speech in another time, and maybe there is some conferences we will ask you to be a keynote speaker in these conferences in the future. Thank you so much, Professor Lin, for the second time.
Yeah. Okay. Thank you very much. Thank you.
Thank you.
Thank you for all. I end the meeting.
لا بهذا الشكل يعني إن شاء الله احنا أنهينا المحاضرة مالتنا. شكرا جزيلا للحضور جميعا. شكرا جزيلا أستاذ أحمد. شكرا لكم جميعا. شكرا دكتور حسن، الحاضرين جميعا. طبعا شكرا جزيلا للسيد عميد كلية الهندسة المحترم والسيد رئيس جامعة القادسية المحترم، وإن شاء الله نلتقيكم في محاضرات أخرى إن شاء الله. شكرا جزيلا.
شكرا دكتور يا حنين.
شكرا.